So, picking up where Sal left off with the video on Monday and what we talked about on Wednesday with the fundamental theorem of calculus part 1, part 2 of the fundamental theorem of calculus states that the integral of a function over an interval from a to b is equivalent to the antiderivative of that function evaluated at b minus the antiderivative of that function evaluated at a. And this is true as long as f is continuous over that interval from a to b. So remember, we've taken antiderivatives before. So the notation for how we're going to be evaluating these from this point forward is, once we've taken that antiderivative, we could rewrite this as the antiderivative of f of x, and we'll use this bar to say that we've now taken the antiderivative of f of x, and all we have to do now is subtract f of b minus f of a. So if we know an antiderivative of f, then we can evaluate that integral by subtracting these values at the endpoints. And that's what we're going to do today. So what we're asked to do here is to evaluate an integral. We're given the endpoints of the interval. And let's use the fundamental theorem of calculus part 2. So we're going to first remember that what we've been given is our function. And in this case, f of x is e to the x. And from there, we can figure out what f of x would have to be. Fortunately, the antiderivative of e to the x is e to the x. Don't forget, though, that there could be a constant. We're going to see why that constant isn't going to matter here in some examples today, but for now, let's generalize, because we can use any antiderivative. So I could use plus c, I could use plus 7, I could use minus 11.5, but you're going to see why that constant's not going to matter here. So let's walk through what we've just discovered we can do. So instead of writing the integral of e to the x over that interval from 1 to 3, I'm going to take the antiderivative and rewrite it like that. Okay, so e to the x from 1 to 3, because it's its own derivative. All right. And so now what this means is I'm going to plug in a 3, and I'm going to plug in a 1, and I'm going to subtract those two results. So this is going to be e to the 3 plus c, and remember that's sort of like my f of b, minus e to the 3, or e to the 1 rather, plus c, and that's like my f of a. When I do this, what's going to happen? So I can drop the parentheses, and I'm going to have e to the 3 plus c minus e to the 1 minus c. And what you're going to see happen here is these constants are going to drop. And that's always going to happen, which is why from the very beginning, I didn't really need to include the plus c. If you want to, you can, but you don't need to, because that constant is going to cancel when I subtract those two values anyway. So what I'm left with is e to the 3rd minus e. And that is the value of that integral. Find the area under the parabola y equals x squared from 0 to 1. We did this before, so just to visualize what it is we're doing here, that parabola from 0 to 1 looks like this, right? Should actually touch there. And so we'll say this is 1, and there's 0, and there's our function. All right, so we're trying to find this area. We did this in the past using Riemann sums. So if you flip back in your notes, you might find a value that's similar to what we're about to get here. But we would have done, I don't know, maybe a right-hand Riemann sum with 4 subintervals, something like this. But that would have been an over-approximation. So what we're actually going to get here is this value, the actual value under the curve, and we'll use the fundamental theorem of calculus to do that. So we're given that f of x is x squared. And so from that, we can determine that our antiderivative is going to have to be an x to the 3rd, right? But when that 3 comes down, if I were to envision myself taking the derivative of that function, it would need to cancel. So x to the 3rd over 3 would be the antiderivative. And I don't need to put plus c, because remember we proved in the last example that that's just going to cancel anyway. So what I'm trying to calculate here is the integral of x squared from 0 to 1. And I'm going to rewrite that as x to the third over 3. That's my antiderivative. And because I've taken the antiderivative now, I'm denoting that with the bar rather than the integral. And so what this means I need to do is I need to plug in the 1. So that's 1 to the third over 3 minus 0 to the third over 3, because I have to plug in each of those values. Obviously, this term here is going to go to 0, and so I'm just going to be left with 1 to the third over 3, which is 1/3. So that's the area under that curve. And hopefully you're noticing that this is going a lot quicker than using Riemann sums and by taking the limit of sums as n approaches infinity. And we're achieving the same result. So let's do one more example in this video, and the reason that I want to show this one is it looks a little confusing because it sort of doesn't appear to be the way that we've seen some of these examples in the past. Don't be stumped by this. This is just another way of writing the integral from 3 to 6 of 1 over x dx. All right, so don't be fooled. That's what that is asking for here. So our function is 1 over x, meaning our antiderivative is ln of x. Okay. So now we can rewrite that integral as ln of x from 3 to 6. So I just need to plug in each of those values. So that's going to be ln of 3 minus, ln of 6 minus ln of 3. Which I could rewrite using my log properties as ln of 6 over 3, which is ln of 2. So that's the value of the area under the curve there.